The first example problem that we're going to cover on 2D motion is a scenario where we have a ball rolling across the table. The ball is rolling horizontally across the top of a table. It rolls off the table. It'll travel through the air, land on the ground a given distance away from the table. And we're asked to find how long does the ball spend in the air and what is the ball's initial velocity when it leaves the table. So the first thing I'm going to do is I'm going to draw a picture of this problem. I'm going to leave a little room up here just so I could write above this. So here is the table that I'm drawing. Here is the ground below. And the ball right here is about to roll off the table. It's just on the verge of leaving the table. And then the ball will roll off the table. It will travel through the air and land on the ground right here. So I could say this is the initial moment, and this is the final moment. Okay, the next thing I'm going to do is I am going to set up a coordinate system. I'm going to place my origin and my x and my y axes. The x-axis will point horizontally to the right, the y-axis will point vertically upwards. So where do I want to place my x and my y axes? Fundamentally, there is no rule saying I have to place my origin, my coordinates in a certain place. I'm allowed to place my axes anywhere I want. However, in practice, some locations could end up being more convenient than others. So I choose that I want to place my x and my y axes. I'm going to put the x-axis to coincide with the ground. So my x-axis will be here, coinciding with the ground. So here is x. And my y-axis is going to point straight up along the edge of the table. So here is my y-axis. Why did I make this choice? Why not put instead of having the origin where the base of the table's leg meets the ground, why not put the origin up here, the ball's initial position or something else? Well, the reason I chose to do that is, personally, I would rather deal with positive numbers than negative numbers. And if I look at this, the ball's position will always have a positive x and y value everywhere throughout this problem. So I chose to do that. There's no reason that I couldn't have put the origin here, and as long as I was consistent with everything else that I label, then that would be no problem. So the next thing I'm going to do is I'm going to look at these two sets of equations. I have the equations for constant acceleration in the x direction. I have the equations for constant acceleration in the y direction. And I noticed two things. First of all, there are 11 terms between all 6 of these equations, but the only term that is common to both the x set and the y set is time. Other than time, none of these equations have anything in common with any of these equations. So what I'm going to do is I'm going to write down all 11 of the possible terms that we might need to find or solve for or whatever in this problem. So I have my initial position in the x initial. I have my final position in the x final. I have v initial x, v final x, acceleration in the x, and time. And of these 5 equations, I have corresponding terms for the y direction. I have y initial equals y final, v initial y, v final y, and ay. So now that we have all these symbols written, I'm going to draw in some numbers from what we're given in the problem, and I'm going to then see, are there any numbers we could right away plug in for these 11 terms? So in the problem, we are told that the table is 1.2 meters high. So this distance is 1.2 meter. And we are told that the ball lands 1.52 meters away horizontally from the edge of the table. So this distance here is 1.52 meter. Now we think about what we know and we realize that if we are ignoring air resistance, which is the case, if you are ever needing to actually account for air resistance, you will explicitly be told that in a problem. If we have no air resistance, then when the ball is right here flying through the air, it will basically be in free fall. And free fall means AX is equal to 0 and AY is equal to negative 9.8. And these are both measured in meter per second squared. When I write the numbers in these terms, I'm not going to write the units. In my opinion, that just clutters the board. I know positions are measured in meters, velocities are measured in meters per second. If you want to write that, that is absolutely fine. Go ahead if that helps you, but I'm not going to do that. So let's look at the picture as we have it right now. Notice that we did not do any calculation yet. We just drew a picture. We wrote some things that we were given in the problem, and then we just wrote out something that we know from free fall from the previous lecture slides. So right away, there are 6 terms of these 11 terms that I could plug a number in for. The ball initially is right here. So what are the x and the y coordinates of the ball's initial position? Well, if the ball is directly above x equals 0, that means the ball's initial x position is 0. And if the ball is 1.2 meters above the floor, that means the ball's y initial position is going to be 1.2 meters. So I could write x initial is 0, y initial is 1.2. We could use the same kind of reasoning for the ball's final position. If the ball hits the floor, and that is the moment the ball hits the floor is considered to be the final position, then, well, the floor is at a height of 0. So this means the ball's final y position is 0. And the ball's final x position, we were given the ball is 1.52 meters away from the edge of the table. So if the table coincides with the leg of the table coincides with the y-axis, we are 1.52 meters away from the y-axis. Our x final is 1.52 meter. 1.52. I'm just going to put a line here to separate the terms just to make this a little bit neater. Is there anything else we could write in right now? Well, we know acceleration is always downward, and we know because we are ignoring air resistance in this problem, acceleration in the horizontal is 0, acceleration in the vertical is negative 9.8. So I could write AX is equal to 0, AY is equal to negative 9.8. In my opinion, it is a very good idea to explicitly write out everything, every term for problems when you solve 2D motion problems like this. Because eventually what we're going to do is we have 6 equations, and it might not always be immediately obvious what equation we want to work with. But if I have a list of terms with numerical values, I could just look at this list of equations and quickly look for what equation has a lot of terms where I could right away plug in numbers based on my list. So are there any other numbers we could plug in, either for any of the velocities or for the time? So I'm going to say, take a minute, pause the video if you want, think about it, and we'll get back to this in a moment. So, are there any other terms we could plug a number in for? I claim there is one other term we right away could insert a numerical value for. and that is one of the initial velocities. So the initial velocity of the ball in the y direction is going to be 0. So I'm going to write that as v initial y is equal to 0. What is my justification for that? Well, let's think about the ball rolling off the table. The moment the ball rolls off the table, the very split-second instant the ball leaves contact with the table, that is considered to be the initial moment. Let's ask, what was the ball doing a split second before that? Well, a split second before the ball leaves contact with the table, it's rolling along the table. So a split second before the ball leaves contact with the table, I'm going to exaggerate this diagram a little bit. The ball was here. Now from the split second before the ball leaves the table to the split second the ball leaves the table, did the ball move upward? Well, no, because the ball was rolling on the table. It did not move upward. Did it move downward? Well, the answer to that question is also no. The ball did not move downward because it was rolling along the table. Moving upward would imply somehow it magically jumped off the table, but that's not happening. We're assuming the table is flat and clean. The ball can't move downward before it rolls off the table. That would be like saying somehow it tunneled under the table, and that wouldn't make sense either. A split second before the ball leaves contact with the table, it is moving to the right in a horizontal, is moving horizontally. Now let's ask what happens a split second after the ball leaves the table. Well, a split second after the ball leaves the table, and when I say split second, I am thinking like an infinitesimal amount of time after the ball leaves the table. So when the ball goes from here to here, well, the ball really hasn't been in the air for very long. It was like for 1 over infinity seconds, a very short time scale. When the ball is in the air for a very short time scale, yes, gravity is pulling it down, but gravity had no time to really act on the ball yet. So effectively, the ball is still going to be moving entirely horizontally. So initially, the ball's velocity is going to be only in the horizontal. So this is my v initial for the ball drawn as a vector. Now, I do not know what the ball's initial velocity in the x direction is, but I know the ball is not moving up, and I know the ball is not moving down. If you're not moving up or down, your v initial y is going to be 0. So I'm going to write v initial y as 0 also. Now at this point, we have every term we could plug in right now. We are asked to find how long is the ball in the air for. That is like asking at what time does the ball hit the ground? At what time does this final moment occur? And what is the ball's velocity when it leaves the table? Now there are two ways I could describe a velocity. I could describe a velocity with a magnitude and a direction, or I could describe a velocity by giving you the x component and the y component. Both of those ways of describing initial velocity would be accepted as correct on an exam, unless I specifically tell you to give me the other one. So if I find this v naught x, I have all the information about the ball's initial velocity. I know v naught x, I'll get some number. Then I give you v naught x and v naught y, and the combination of those two values is the answer to what is the ball's initial velocity. So these are the terms we want to find ultimately for this question. So now what I'm going to do is I'm going to look at these 6 equations. I don't know which equation is going to be useful immediately, but let's look at these equations, pause the video if you want, and see if there are any equations where you could just plug numbers in except you have one unknown, and that one unknown is either this guy or that guy. So if I look at these equations, and the first thing we're going to solve for is the time. Also the fact that what time does the ball hit the ground is part A of this question that strongly suggests we will be wanting to solve for time first. So as a problem-solving strategy, usually if you're asked to find the time in the air, you will be solving some equation related to y. There's no guarantee that this will work, but it's a good place to look first. So I look at these equations. I want an equation that has time explicitly written on the y side. So this last equation does not have time written anywhere, so this last equation probably will not be very helpful to me right now. I could look at these other two equations. I could look at the second equation. I know v initial y, that's good. I know acceleration in the y, that's good. I do not know v final y. So if I don't know v final y, yeah, there's time, but this would be two unknowns. So I don't know if I'll need this equation eventually. Let's look at the first equation. If I write y final is equal to y initial plus v initial y t plus 1/2 ay t squared, I could look at this and I could ask, do I know y final? I look at that chart I have over there. Yes, I do. Do I know y initial? Same answer. Do I know v initial y? Yes, I do. Do I know t? Well, that's really what we want to find. Do I know the acceleration in the y direction? Yes, I do. Do I know t? Again, no, but t is what we're looking for anyway. So looking at this equation, I could plug a number in everywhere except for t, and t is what the question is ultimately asking for. So this will be very useful to me. So y final is 0, y initial is 1.2, v naught y is 0. I'm going to write every term out, and then even though we have a multiplication by 0, and then in the next line I'll get rid of it. So 0 times t plus 1/2 ay negative 9.8 times t squared. Okay, 0 times t, this term is going to be 0. So what I'm left with is 0 is equal to 1.2. Negative 9.8 times 1/2 is negative 4.9, so minus 4.9 t squared. I bring the negative 4.9 to the other side, so I get 4.9 t squared equals 1.2, and divide 4.9 from both sides. I get t squared is equal to 0.245. And I take the square root of both sides of this, so square root that, and then I get t is equal to plus or minus 0.5 seconds. Now, mathematically, I have two solutions to this equation, but I need to now think about what these solutions are telling me and actually connect them to the real physical world. We say t equals 0 is the moment the ball rolls off the table. Does the ball hit the ground 0.5 seconds after it rolls off the table, which is the positive solution, or does the ball hit the ground 0.5 seconds before it rolls off the table? That would represent the negative solution. The negative solution makes no physical sense. You won't hit the ground before you roll off the table. So even though I have two mathematical solutions, I will throw the negative solution away as being unphysical. So I could say the time that the ball hits the ground is 0.5 seconds. Now, for part B of this problem, we are asked to find the initial velocity in the x direction. So what I'm going to do here is I have a new piece of information that I can work with that I have at my disposal. In addition to the 7 terms we initially had, we initially knew the 4 positions, the 2 accelerations, and v naught y. I now have an 8th piece of information. I know the time that the ball hits the ground. So I will use this piece of information. It's just as good as having x initial, x final, and any of the other pieces of information. So to find how far the initial velocity of the ball when it leaves the table, we have 3 equations here. So if I look at these 3 equations, I want to know about something in the x direction, so I probably will need one of these on the left-hand side. Which one do I want to use? Well, there's a v initial x, there's a v initial x, there's a v initial x. So right now it looks like all the equations might be useful to me. The second equation is short. Let's look at that equation. Vx final is Vx initial plus AXT. Well, I don't know Vx final. This is really what I want to find. And AXT is just 0 because I multiply AX is equal to 0. So this term is just going to be multiplied by 0 and not matter. So I know that the final velocity in the x is going to be the same as the initial velocity in the x, but that doesn't help me get a numerical value for initial velocity in the x. So this second equation is useful in many scenarios, but this scenario is not one of those times. What about the equation below it? Well, this looks good. I have an x and an x initial. I have numbers for those. Let's see what I get. Vx final square equals v initial x square plus 2ax, x final minus x initial. Well, this looks a little bit more promising, but I do not know what Vx final is. Vx initial I really want. I know what these numbers are, but the problem is this entire term here is just going to be equal to 0. Because even though I have numbers, ax is again equal to 0. And I multiply that by 0, and I'm left with what I had previously, a statement that the final velocity is going to be equal to the initial velocity. So we found that these last 2 equations will not be helpful to us. Well, we only have 1 equation left, so this must be the one that will work. So for this, let's see, we have x final is equal to x initial plus v initial xt plus 1/2 axt squared. Do I know x final? Yes. Do I know x initial? Yes. V initial x, that's really what we want to find. I know time. I did not know time before I did part A of the problem, but I know time now. I know acceleration in the x, and I know time. So again, I'm at a scenario where I can plug numbers in everywhere and hit enter on the calculator and be happy. So 1.52 for x final. Again, I'm going to write out every term in this line, even the terms that are 0, and then in the next line I'll get rid of the terms that are 0. X initial is 0. V initial x is what I want, so I'll leave it as v initial x. T is 0.5 plus 1/2 times 0 times 0.5 squared. So this term is 0. This term over here is multiplied by 0. So what I'm left with is 1.52 is equal to 0.5 v initial x. And if I divide by 0.5, those two cancel, and I'm left with 1.52 over 0.5. I find v initial x is equal to 3.04. So I have v initial x is 3.04. So at this point, I am done with the problem. The answer to part A is 0.5 seconds. And the answer to part B is v initial x is 3.04 meter per second. And v initial y is 0 meter per second. In order to get full credit on this problem, for part B, you need to include both v initial x and v initial y, because a vector has a magnitude and a direction. So you could write v initial x is 3.04, v initial y is 0. Another way to correctly answer part B would be to say the ball has a velocity of 3.0 meters per 4 meters per second, moving in the positive x direction. And so if you were to explicitly state what direction the ball is moving in, and then tell me the magnitude of that vector, that would also be acceptable.